Okay, so this is example 2.3e from the companion to the textbook. In the textbook is example 2.20, and the name of the example is components of a force in directions normal and tangent to a plane. And here's the exercise. So you have a plane. It's defined by these 3 points, A, B, and C. And you've built a house on this plane, and the house has a mass of 95 megagrams, which is 95 times 10 to the 6 grams. So you have to be a little bit careful of the units there. And you're worried about the house sliding down the slope, so you would like to know the component of the weight of the house that is in the direction normal to the slope, and maybe more importantly the one that's in the direction parallel to the slope. And you'd also like to know the vector components. So the part A is the magnitudes of those vectors, and part B then is the actual vectors. And then part C is what is the distance between the origin, so point O, and the plane, and the shortest distance there. So that's the exercise. And if you want to go attempt the exercise and come back, then we'll go through the solution. All right, so as usual, we'll do the solution in sort of 2 parts. Right? The first part is let's figure out the equations that we need to solve, and then the second part is let's go solve the equations. Right? And the second part is where a computer program like Ease really comes in handy. The first part, you're kind of on your own. You're gonna have to do that by yourself. So yeah, let's go through part A and move on to parts B and C then. So part A is try to find the components of the vectors of the weight that are parallel to and perpendicular to the plane. So the first thing we want to do is come up with 2 vectors that are in the plane, and we know that that's an important thing to do because we know that the cross product of those 2 vectors is going to give us a vector perpendicular to the plane. So 2 vectors that are in the plane are RAB, and that's just the point B minus point A, and RAC, right? So that's point C minus point A. And you can see those drawn here. And then let's define a vector N that is the cross product of these 2 vectors, right? And according to the right-hand rule, that cross product is going to be pointing up, away from the plane as I'm drawing it here. So that's pretty much the only new thing here is getting that cross product. After that, it's very similar to the last example that we did. We want to figure out the component of the weight that is parallel to this vector N and perpendicular to it. So the weight is in the Z direction, right? So it's just M times G times the unit vector in the Z direction, which is K, and is negative because it's pointing down. So I've drawn it here. So if I want the component of the weight that's normal to the plane, I would just take the dot product of this weight vector and the unit vector N. So I'm just going to take the dot product of W and then N divided by the magnitude of N. So that's what I have here. And then because Wn, Wt, and W make up a right triangle, you know that Wt is just the square root of the magnitude of the weight squared minus the magnitude Wn squared, as I've done here. So those are the equations. I guess there are 6 equations. They're sequential, right? So we're not going to need to use Ease's iterative solving capability. We just need to go ahead and enter those into Ease. Okay, so here's the equations window of Ease. The first thing I'm going to do, because I know that I'm going to want to use the built-in constants in Ease, in this case gravity, I'm going to set the unit system, which is always a good idea. So that's what this dollar unit system directive and I want to be using SI units, so I'm going to get gravity in meters per second squared. And then I'm going to enter the inputs for this problem. The inputs are the mass. So the mass is 95 times 10 to the 6 grams. Grams is not the base SI unit of mass, so I'm going to go ahead and convert that from grams to kilograms. And then the other input are those 3 coordinate points that define the plane. So they have x, y, z coordinates, so they are like vectors. So we'll declare them to be vectors and then assign these points according to this drawing here. All right, and then we're just going to follow along with the equations that we derived. So we need 2 vectors, RAB and RAC. I'll declare them, and then I'll calculate them. So RAB is point B minus point A, and RAC is point C minus point A. And we can look at these as we go, so it's good to solve and look at the solution window and make sure that the vectors obey our intuition. Again, at some point here soon in the next video, we'll talk about how we can plot vectors. And at that point, it's really handy to go ahead and just plot these to look at them as we go and make sure that they are looking the way that we would expect them to look. So the next equation is taking the cross product of these 2 vectors, and that is where we will use the VectorCross function. The VectorCross function takes in 2 vectors. So in this case, we're going to take the cross product of RAB and RAC, and that will return for us a vector that we'll call n. So that's the normal vector. And again, when we can plot these vectors, we'll be able to actually make sure that n is perpendicular to the 2 vectors in the plane, and also behaving according to the right-hand rule. We're going to define the weight vector according to this equation. So the weight is the mass times gravity. So here's where I'm using that G hashtag, the gravitational constant. And the coordinate, the unit vector that defines the direction of the weight vector is just minus k, right? So vector assigned 0, 0, minus 1. Okay, then we have the equation here to figure out the magnitude of the component that is in the direction normal to the plane. So I'm just taking the dot product of the weight with the unit vector, and the unit vector is n divided by the magnitude of n. So that gives me a magnitude that is, let's see here, 460, minus 809.6 kilonewtons. So it is negative, which makes sense, and it's less than the total weight, which is 931.7. Okay, and then we'll use this equation to get the magnitude of the weight that is tangent to the plane, and that's just this equation right here, and that gives me 460.9 kilonewtons. All right, so that's part A completed. In part B, we're doing basically the same thing, but now we're going to turn these magnitudes into actual vectors, right? And so that's not hard. This is kind of what we did in the last example. We know, for example, the magnitude of the weight in the normal direction, and we know what the normal direction is, right? It's n normalized by the magnitude of n, so it's just Wn times that unit vector. So that's what I did right here, and that gives me this vector right here. And again, if I could plot it, I would be able to visualize it a little bit better. And then this vector equation, W equals Wn plus Wt, defines Wt, right? Because we're using e's, we don't have to explicitly solve for it. It'll solve for Wt here, and it gives me that equation right there. So that is part B. And then the last part of the problem, it asks us to figure out the distance, the shortest distance between the origin and this plane. Right? And this is something that we will do by figuring out a vector that goes from the origin, to any point on the plane. So it can be literally any point. In this case, this ROA, right? And then we'll take the dot product of that with the direction normal to the plane, which again is our n divided by the square root or the magnitude of n. So that is going to give me the distance, and that's a pretty easy equation to enter into ease. I've done it right here. And if I solve this, what I find is that the distance is 52.14 meters. So the origin is 52.14 meters away from the plane.